Yeah. As the angle gets bigger, the time and max height both got bigger. Absolutely, directly related. What else? What else? Some other piece. Somebody else. What other piece? There's something else that we also talked about. And this was not necessarily directly related, but there was some sort of a pattern.
The range was like, it was weird. It wasn't directly, but it was, at some points if you put it higher, it would be longer. But then also if you put it all the way up, it would be short.
Yeah, so for the range, you notice that if you wanted to get the most out of your x dimension, you kind of had to tweak that angle. You kept raising it up until you got to around like 40 or 50, a lot of you noticed. But then when you went beyond around 40 or 50, what you started to notice was that the range started to decrease. So there's that like halfway point between 0 and 90, which is around 45. And theoretically speaking, that would be giving you your max range. Actually doing it with air resistance, it's a little bit different. It's not exactly 45, but you should have figured that it was around between 40 and 50 when it comes to degrees. And what we'll see here is we're going to start with 65 as our angle, and then we're going to lower it a little bit, and it's going to shoot further and further. John, could you slide up to this empty seat? Because I'm realizing that it might go a little bit further, and I don't want to hit you. Jake, just be aware. Just be aware when we're launching this. We're going to launch in a minute, but it's not going to land that far, but it might go as far as the desk there. I'll try to jump in and catch. Now, one other thing to notice is this. This is a schematic of that device. I drew it very simply. I drew that little red, like it looks like a little platform, because the device, if you look over here, and point where the marble is so you can see it. See where the marble is? It doesn't start at ground level. Just like the cannon, remember the cannon in that lab? It kind of started above ground level a little bit. You remember your delta y was always negative 1.2 every time? Remember when the height at the top, it kept showing negative 1.2? That was because the cannon started here, and it ended a little bit below that. So every time it would go like this, it would come down 1.2 meters below where it started. So it kept showing y equals negative 1.2 because the starting point was above the ending point. That's what's happening here. This object is being launched from a certain height, and it's ending over here. So this is the height at which the device uses. 0.14, let me make sure that's right before we go. Yeah, 0.146 meters above. So Anthony laid out some blue tape and lined it with meter markings. So we have 10th meter markings along here. So what we're going to do is this. We're going to launch it a few times. We're going to go through some concepts, but then we're going to actually launch it, record the range, and prove mathematically that it's the exact same answer that we got here. Okay, because the device is able to measure precisely the initial velocity. Because it's a sphere, there's very little loss to air resistance. So our answer should be pretty close to spot on, almost exact. And what's cool actually is that if you do it enough, you could actually figure out where it is, and you could guess where it's going to land based on the math. So one of the things I was looking at this online, I was trying to read some cool ideas about this, was actually being able to estimate where it would land. So placing an object at that landing zone based on your calculations and seeing if it comes up close. So we'll go through both of those ideas. So first, I'm recording this on purpose actually. And if somebody wants to, Juliet, can I ask you, because you're so close over here, could you take a video of this so when we're looking at it later, if you guys are looking, you see exactly what we're doing? And to take a video, all you have to do here, and you're going to hit new video. So it's going to appear like that. And once you hit record, and you'll see on the screen, you'll be able to record what's going on here. Let's see. Maybe it's actually too close. Where's the actual camera? Down here? The camera's down here. Yeah, actually, maybe should I go back over here? Well, I want to get the profile of the launch, really. You know? Caroline, you want it? Do you mind? Yeah. If you want to just stand over here maybe and take a video like this. Okay? And all you got to do is hit record down here as soon as we're about to launch it, just so we have an idea later on of what we're physically doing. Okay, if you don't want to be in there in the video, you don't have to look, or just maybe move over a little bit. Julia, you're kind of in the video if you don't want to be. Obviously, it's up to you guys. Okay, we're good on there. So what we're going to do again, we're going to launch this. It's at 65 degrees. We're going to get an idea of where it landed. I need you over here, ladies, to try and get an idea of exactly where it landed. Now, we have this other tape here that leaves a mark. And it leaves a mark on the tape where it landed, but unfortunately, it's not very consistent in its left to right motion. So I'm a little bit nervous. We might use that in a little while, but let's see where this lands first. So are you at 75%?
Yes.
Okay. So safety first, thank you. And to get the exit velocity for this program, all you have to do actually is hit play on here. And what it'll do is there's a photo gate in here, there's a photo gate here and here. It'll sense the ball moving past the first photo gate, and then the second photo gate, and it'll approximate the velocity when it exits. Okay? Alright, you want to start recording that? So we have it? Yep, when she's ready. So where were we? Approximately here. So we're looking at around 2.2 meters for the first one. Now, this was at 65 degrees. Let's get the same thing. Let's change the angle. So we'll put the angle this time. We'll drop the angle to 55 degrees now from 65 degrees. He's going to use the same amount of force because this is a pressure gauge here. So all you're doing is putting pressure into it. So if Anthony doesn't change the pressure, the exit velocity should remain the same. And that's the thing we have to keep consistent is the exit velocity. If the exit velocity is the same the whole time, and he just lowers the angle from 65 to 55, it should go a little bit further. And then as it gets a little bit lower, it should go even further until he passes that 45 mark, and then it would go actually shorter. You would have like a little short path here. Okay, so the goal right now, and this is where the inconsistency can come into play, is to have the same amount of pressure, the exact amount. You can bleed it off of that, right?
Yeah, it bleeds off all of that.
Perfect. All right, and now we'll run this again to see. So it turned out, somebody jot this number down, please. That the speed was 5.22 meters per second for the first try. 5.22 meters per second, you got it? And then the range was 2.2 meters. So let's say x equals 2.2 and vi equals 5.22. Just get that data down real quick so we can compare it to the next one. Okay, so now again we're at 55. We're going to attempt to have the same exit velocity. This should go further. So I might have to catch it over here. It might go off the table based on where I'm at. Okay. Yeah. So I put it all the way out here. So oh, try it again. Try it again so we get the velocity again. So it looks like we're going to go even further. So let's do this. If this is not, is that locked? Unlock that wheel right there. It is? One of these is locked. Try and unlock it. Is that unlocked also? Click it up. Let's connect these. This tape. Maybe extend this a little bit further. I didn't expect it to go this far, but this is fine. This is good that we see this.
Didn't shoot all the way across.
I don't know, actually. I mean, 45 would give you the max range, and the maximum pressure you can apply is on there. So we could try that and see how it works.
I think it was really far when you tested it for the first time.
Right? It went pretty far.
Yeah, it shot from that table all the way over to the radiator.
What?
What's up? I don't know. Oh, wait.
Here's the
Nah, do it again. Nah, you sure? Yeah, do it. Do it. Yo, you know, I didn't want to snap on the board and they got TH2
Alright? I don't think we went further than this, right? Am I good? Did it that much further than where I'm at now?
Wait, is it on Facebook? I mean,
Let's start that for now. Here we go.
YouTube?
Again, same thing. Same thing. Try to identify where it lands, if you can see. Right here. Alright, so let's say this one is going to be x equals 2.6, approximately 2.6 for x. Exit velocity of?
5.
Yeah, perfect. 5.24. Last one 5.22. So as long as Anthony's consistent with the amount of pressure he applies, this will stay the same for velocity. Now the last one we're going to do is going to be 45 degrees. And we should get the most range out of this. Let me mark off his last view in case we have this. X in this case was, what did we say?
2.6.
There you go.
What do you do?
Alright, we got 3.7 meters. Let's hope we don't exceed that value. So, Ryan, ready? Be careful.
You know what? I'm trying my
You
best
will
over
have
here.
some, try
I
fast.
don't appreciate that.
So we got 45 degrees, same pressure, everything. Okay? Where were we? Right here? It landed over here, I know that, yeah. Okay, so we're between around 2.9, let's say 2.9 for now. 2.9, what are the exit velocity? 5.2, so we're pretty solid again. And this again was about 2.9 for the actual x value. What did you notice? What did you notice right away? Probably less hang time. Okay, this was a little bit lower. It went further, but it wasn't up in the air as long. When he altered that angle and increased it in the beginning at 65, we saw a lot more height, right? We didn't see as much x displacement, whereas the last one did. What would happen now if we went below 45? Let's do that just for the sake of it. Oops.
Yeah.
What's going to happen if he goes below 45 now?
The hang time is gonna decrease, and like how far it goes is also gonna decrease.
Exactly. There'll be less hang time and less horizontal displacement. Okay, so let's try to make it significant. Go to 30 degrees. So it's clear that we know we're definitely below that. So he's going to drop to 30 degrees, and we're going to see a low line drive. This was, remember that part of the lab that said the quarterback decision? It was like, which way would a quarterback throw the ball? Would he throw a deep fly, a deep Hail Mary, or a low line drive? It depends on how far he's throwing. So in this case, this would be like a low line. Trying to get same pressure again?
Yeah.
It's a good thing we have Anthony's our expert with this. So I actually hit this right here. So that only went to about 2.5. And our angle was 30 degrees, and our exit velocity 5.22. Awesome. Caroline, you can pause that now. Thank you. Okay, so we all, what's that?
What was the velocity?
The exit velocity was 5.22.
Oh.
It's pretty much been the same almost every time. The velocity really has not changed because Anthony was very consistent with what he chose here.
Hey.
Wait, but is that the max pressure?
No. So you want to see how far to go?
Yeah.
Yeah.
Let's get it to 45 and come all the way up. This is just for the fun of it. We're not going to, it doesn't matter the data. It's probably going to end up over here, so be careful. So that was at the whole time, I think 75% pressure.
I haven't seen it.
The max.
That was about
Looking at the
80
video.
8 and the max is 100 you put in?
No, I think it's just we'll see.
Heads up, I'll give you that back up for sure.
Imagine they tell me which is
It's going to about 100.
140?
Yes.
So this might go really far, so heads up. So I'm building it to like, I'll block it for the window. I need something like, give me a folder. Like a book or a folder. I want to hit the face.
Yeah, just that.
I'm gonna block this.
Can you record this?
What's the difference? Let's do it once first before we start recording. So is that 45?
Yeah.
Alright. You're ready. Let's hope it doesn't go too far. Oh. No, it's not my fault.
I want to go far too.
First of all, that's right. My guess is that there's probably a safety valve, and that even though the pressure continues to increase, it's not going to apply all the pressure.
I might be able to turn it further in a second.
Try one more time. I want to get to the math again, so let's finish this last one, and we're going to go back to the math. What's that? I thought you were going to be based on.
I think it's like fire. It's like.
That's why I said give me a book, just in case like the math.
Yeah, like totally. And you always say where those
That's the max. Okay, I wasn't at the max. This is at 190.
Let's see.
I'm not
This
gonna
is
do
as
it.
far as I'm getting.
Yeah. Make sure the marble's all the way in.
Yep.
Okay, so there's an actual vacuum there.
Ooh.
That was pretty far.
Yeah.
That's not bad. What are we like here? Like 4 or 5 meters. It's probably neat not to go further because the classroom's confused. Alright, cool. Very cool. Let's go back to the front for a sec. Focus back on the front. Very useful. Yeah, that's fine. Grab the table back. Take care of a little bit of that over here, though, so don't take the staples and throw mine. No, I want to leave everyone.
Hello. We're here in physics. This is going to be a Moodle, so.
Awesome. Thank you so much. If Caroline's, no, she's not free either. All right, we'll figure that out. Thank you, Caroline.
I've been talking to recording because it's still on.
Ah, nice. What? Oh, so ask, yeah, if you can come down. That'd be great. Like, and you can wait like 5-10 minutes into the period because they have to take a quiz still. So 10 minutes in if you can come down. Thank you, Ed. All right. This was great, guys. This was great. Let's go on. Let's talk about this for a little while now. So I need some of that data real quick. Okay, I need some of that data. So we got VI, we've got theta, and we've got X. Theta, we started 65, 55, 45. I know that. What did you get for your 3 X's? What were they, Matei?
2.2,
Okay.
2.6,
Okay.
and 2.9.
All right, so clearly what happened, obviously, the range increased because the angle was getting closer to 45. If we went below 45, which we did, we saw a huge decrease in the range. Did we take data for that or no? We didn't, right? Did we have an X value for the 30? Anybody? Did we write it down?
Yeah.
Yeah.
2.5. So when it was around 30 degrees, it was around 2.5. And the VIs were all pretty much 5.2?
Yeah.
5.22, 5.24. So for the most part, we could just say 5.2. And that's the idea. We wanted that to be consistent. If you changed the VI, you would change X, and it wouldn't be a function of the angle anymore, right? You would have two variables that were affecting the outcome. The angle affects the outcome and the velocity. So you can't vary both, or else you don't know which one has the impact. Clearly, if you have more velocity, what's going to happen? It's going to go further. That should be obvious. It should be common sense. Think about it. If you throw something harder, it goes further. So the velocity is directly related. So we kept the velocity the same the whole time. We held the velocity constant so that our variable of interest could be theta. Okay? And what did theta affect? It affected x, the range. Now, it also affected the hang time and the max height, right? We saw that also. We saw that as well. Now, let's go ahead and check this mathematically first, that these answers are reasonable. And then what we can do is we can come up with a max height value. And then think logically and look back at the actual picture and say, is that reasonable what we get as an answer? Okay, because on the video we could probably actually see it. The video that Caroline recorded, you could actually probably see the path of the projectile and probably mark off the max height and get an actual value. It's very difficult to do that though during the lab. The only way to really do it would be to like hold a meter stick up in the background so you see where it crosses the meter stick. Does that make sense? Okay, hold a vertical meter stick up or else you really can't measure that value. So let's go ahead and let's take a look at our value for 55 degrees. We'll use this one as our interest right here. Okay, so let's start a problem. And we were told earlier that this object, so we have x and we have y. We're going to go right to our table like we've been doing all along. We're going to use the one with 55 as our value. So we're told that theta is 55 and that VI is 5.2. Okay, and the x that we got was 2.6, and we're going to see, is this correct? That's what we're going to try and figure out. So we're going to assume we don't know x for now. We'll calculate x. No, it's fine. But put x equals 2.6. But put a question mark next to it saying we're verifying if this is true or not. So if the angle is 55, and I want to start with my x and y components of velocity, I start with the velocity initial times the cosine of 55, the velocity initial times the sine of 55. So that's my beginning part right away. Okay, this is the first step. For all these problems, when it's launched at an angle, start right away by doing this. Now tell me, without calculating, some of you are doing it, it's good, no, you can do it, but without calculating it, how would you know which answer is going to be bigger? V bar x or VIY? Which is larger? Which is larger, am I?
VIY.
Why?
Because the wind have to travel more vertically than horizontally.
Yeah, because the angle is
Above 45.
above 45. Very good. When the angle's above 45, your more velocity is in the y direction to start. When it's below 45, more of the velocity is in the x direction to start. So you can calculate these two values now. What do we get for v bar x? 5.2 cos 55. Just call it out, please. Annabelle? 2.98. And the other? And the other? 5.2 sine 55? 4.25. All right, so I don't need these values anymore. I'm going to cross them off. But you can still see them, so I didn't cross them off too much. But once I calculate them, you don't need to write them twice anymore, so don't confuse yourself. Clearly, as Amaya pointed out, more of the velocity is in the y direction because it was above 45 degrees. The actual velocity was 5.2, so these numbers are both below 5.2 because 5.2 is the overall velocity. These are the components of velocity, which will always be smaller than what you start with. Okay, now, the y value, we were told that it started, if you recall, it started from a height of 0.146 meters, right? Remember, it started a little bit above ground, and it landed on the desk. So the y value would be negative 0.146 meters. Why is it negative? Why is it negative in this problem here? Yeah, it started, if you recall the diagram, if you want to think about what the diagram would look like, let me get rid of the state at the top so I have more room. If you want to think about what the diagram would look like for this, here was the diagram. It was launched here, and it ended up a little bit below where it started. So this value is above this value. Okay, it started in the cannon. The cannon was like a little container like that, right? So this differential was 0.146 meters. So as a result, since it started up here and it ended below where it started, the y displacement is negative 0.146, which you might say that's negligible and just put 0 down. But that would probably change your numbers a little bit in the end. It would probably alter or affect your answer. Okay? So this is the diagram we have. I'm going to erase the diagram. You've all seen it already. I'm going to erase the diagram. All right, now, after that, we have to start thinking about what else we know. What do we know in both directions always? We always know something in both directions.
You know the acceleration.
You always know it. What do you got?
The acceleration for x is 0, and
Good.
the acceleration for y is negative 9.81.
Good. Again, keep practicing. Keep doing your homework. This will get easier. You will memorize these things. You'll remember them every time. So you got VIY. We got y. We got AY. Well, if we want to figure out what x is over here, that's great. But what else do we need to find x always? What else do I still need to find out what x is? Time. So I can't use the x direction, so I'll jump over to the y direction. If I was given x, in this case we were given 2.6 because we measured it, but we're actually trying to calculate to verify that. Okay, so we go to the y direction and we use this formula. Okay, we use this formula in the y direction always. Okay, we're going to use this a lot when we're trying to calculate time. We're trying to calculate time. Now, we're going to run out of time, no pun intended there, in about a minute or two. And when we do that, we're going to pick up with this tomorrow. Okay, we will pick up with this tomorrow. But I will happily tonight, if you want more practice, send you some more examples to practice tonight. Okay, so I might make like a worksheet up for you to practice. I'm not going to collect it. It's going to be practice for you to do more work with. Okay, so if you think you struggle with the homework, you need to practice a little bit more, okay? So keep checking your emails tonight. I'll try and send something out for you to practice. The y value, negative 0.146. VIY is 4.25 times t minus 4.905 t squared. Again, this should also be second nature now. Half of negative 9.81 will always be negative 4.905. So we got to move everything over. Okay, and we solve this quadratic. There's a t there, I promise. There it is. Okay, we solve this quadratic either by the calculator or by the quadratic formula. It does not matter which one you choose. It does not matter. Okay, I'm telling you now, though, that I think one of your times will end up being negative, so you'll know which one to reject right away. Okay, for a problem like this. Can somebody do it on, who knows how to do it on the calculator with the graph? Can you do it quickly for me so I can get the numbers? Okay? Yeah, you got the quadratic right here. Try to plug this in y1, please, and give me the x-intercepts the way we've been talking about, how to solve this with the calculator. I know I'm getting two answers, so I already wrote down t equals twice. And I want verification, so even if one person gets it, others still continue, please, to verify. And you're probably going to get one of your answers where it's negative, the x-intercept, and one of them positive. If one is negative, it doesn't matter.
What's the step?
So you press second, calculate. You want to find the 0, enter. Now, you want to get something to the left of that root and something to the right of it. So the left bound. So keep going a little bit further to the right. All the way. A little more. Enter. And press to the right again. Keep going, past the root, pass it, enter. Enter one more time. So Caroline got 0.899. Did anybody else get that? Okay, 0.899 seconds. And the other answer was a negative number. I don't care about that one. Okay, I'm going to reject that answer. So we take 0.899, we plug it into the x direction now. I'm happy to go over this individually if you couldn't get that. Take 0.899, plug it in. We have the following formula. If I want to find out what x is, I take the 2.98 for v bar x. I plug in the 0.899 for time. So multiply 2.98 by 0.899. Move that up by multiplication. What do you end up getting for x?
26.79.
Careful. It should be 2.679, I think. You have 2.98 divided by 0.899 times 0.899. What do you get? What do you get? Multiply these two. What do you get? 2.67? Not bad, right? What did we say? We said around 2.6 when we measured it. Like hypothetically, we eyeballed it. Tomorrow we'll continue. We'll talk about max height. We'll talk about time to max height. All those other pieces. Okay? Bring this tomorrow. Be ready for tomorrow. Okay? I will definitely send you some stuff to practice tonight if you want to practice a little bit more. What I want to do now with this problem is go over the concept of, can we figure out what the max height was? We could have estimated it. Remember in the video, I was telling you guys how if I held up a meter stick, if you had put a meter stick up in the back of the video and Caroline was taking the video, we could have probably paused and seen where it crossed. Does that make sense? We could have seen where it crossed on the meter stick to give us the max height. But it's difficult to do that because depending upon the angle we were launching at, the max height occurred at different locations. Right? If I launch at a really high angle like this, the max height is going to be close to the beginning right here. But if I launch at a low angle, max height is all the way out here. So the meter stick would have had to been placed at a different location depending upon the angle. It is something we can do to check that. But what we want to do now is just mathematically figure out how to find that max height. But we still have to use the same information that we had earlier. So tell me, I'm going to start this problem like it's new. Tell me what was our information. What was the angle that we chose? What was the angle that we used? What did we do? I think we did 55. We did 3 trials, but then we used 55 to check the data, right? I'm gonna stick with 55 then, just to be a little bit consistent with what we're using. So let's say theta is 55 degrees. What was our VI? Does anyone remember that?
Well, for the X, it was
Just in general, the general VI. I'm gonna redo it. Thank you. There we go. I remember being around 5.2. I'm going to redo the VIX and VIY on purpose, okay? So that's our angle and that's our launch velocity. Do we have anything else? There was one other piece of information. There's one other piece. Yeah, it started at a height of 0.146. Now this is going to be a little bit tricky. So I'm just going to put on the side starting height. Because it turns out that doesn't represent a variable. And I'll explain why that is in a moment. Starting height is 0.146 meters. God bless you. Okay, and I'm just jotting that down as a side note for now. And we'll see where that comes to play a role in a little bit.
Don't you also need the X?
In this case, we're not going to need the X. That's a really good question, actually. The question was, don't you also need the X? X being 2.6 or 2.67. We don't need that for this problem, and I'll explain why. We'll see at the end that the X could have been used, but we don't actually need it. All right? So there are 2 ways to find the maximum height. There are 2 ways. One way is to do what Ernest mentioned, using the X, just cut it in half. Think about it. Take the X, or the time of flight, and cut it in half. Because we assume that a parabola is symmetric. So if I take the full time of flight, did we get a time in the previous example yesterday?
Yeah.
What did our time turn out to be?
0.89.
0.89. So that time, I need you guys to focus up here and listen and look. That time is the time from here to here. So theoretically, if I want the midpoint and I want to find the height at the midpoint, I could cut that time in half. That time itself could be cut in half. We could go ahead and look for the height at that time exactly. But this problem was not perfectly symmetric. Remember, it started at 0.146 and it ended on the ground. So there's not perfect symmetry. So theoretically, although it's a good estimate, we can't really just cut the time in half and plug it into y equals VIT plus 1 FAT squared. We can't really do that. And we'll check it in a moment to see how there is a little difference in the answer for max height depending on the method you choose. The method I would like you to choose is this, right here. Remember, and this is hard to visualize. I'll give you a little visual with the markers. When this object is launched initially, it was launched in both the x and y direction. So there was some velocity in the x, some velocity in the y. As it moves up, what happens is this velocity becomes less until it's 0. And all the velocity at the top is only in the x direction. remembering that this number is a constant. This is a constant. Why is this constant? Why is v bar x constant? Why is this not constant? Ryan?
Well, there's no air resistance, but there is gravity.
Exactly. No air resistance, so no acceleration. That's what Ryan was saying there. No air resistance or no acceleration. But in the y direction, there's gravity. So gravity is an acceleration pulling it down. Think back to section 3.1 and 3.2. If an object is moving in the positive direction and acceleration is negative, what happens to it? It slows down. Remember this chart we filled out? Slows down and speeds up? Well, look at this. The initial velocity in the y direction is upward, positive. Yet the acceleration is negative. So what's happening in the y direction? It's slowing down. Whenever these signs oppose each other, it's got to slow down. So again, just to give you a little visual, it's moving up, it's moving up, it's moving up. This vector is getting smaller and smaller and smaller, and then it doesn't exist at the top. There's no vertical velocity at the top. But the horizontal velocity is the same at any instant along the path. You had a couple conceptual questions on your last homework, and a couple of you guys got mixed up on this. One or two of them talked about the horizontal velocity and said, what is the horizontal component of the velocity at the starting, at the top, at the end? They're all the same. This number, 14.2, is the same throughout the entire problem. V bar x does not change because there's no acceleration to change it. The only thing that could cause your velocity to change is acceleration. That's the definition of acceleration, a change in velocity over time. So if there is no acceleration, there is no change in velocity. Thus, this is a constant the whole time through. So the answer to that homework was that, yeah, whatever the starting velocity is for the x component, Vix or V bar x, is the same throughout the entire process. It's moving with the same velocity that way. But the y direction, again, you have velocity of 11, then maybe it's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, no velocity. And then what happens to the velocity? What happens after it reaches this, George?
It decreases.
Yeah, and it decreases, becomes what kind of a number?
Negative.
A negative number, very good. Remember, your velocity is positive to start. It's decreasing the whole way up because acceleration of gravity is negative. And then when it reaches the top, it starts to speed up in the negative direction. So the velocity is technically, as George said, still decreasing, meaning it's getting more and more and more negative. You could say that the speed is increasing in the negative direction after it reaches max height. So what I want to do here is determine max height for this problem. So I'm going to look at this problem, and you know what I'm going to do? I'm going to do this. I'm going to say, let's just look at the first half of this problem. That's what we're going to do now. And this number now, we don't even know what this number is. Ignore it for a moment. We don't know if there's symmetry at all. In this problem, there wasn't perfect symmetry. But we do know that this starts at a height of 0.146. Here's the ground, right here. Here's the apparatus that's launching the projectile. And we know it starts at a height of 0.146. If it gets up to like 9 meters as a height, is that going to be my answer?
No, because of the 0.146.
So what do I have to do, Brian? Yeah, I'm going to have to take this away afterward. Think about it. If this gets to a height of 9 meters, how far did it actually travel? It would be 9 meters minus off this 0.146. Okay, that's actually the max height. So let's go through this problem and do it. So we go to the x and y direction as always. Okay, we go to the x and y direction. In the x direction, we have v bar x. And in the y direction, we have VIY. Again, what are they? I'm doing this to emphasize. You should know this already. You probably have it written down from the problem yesterday. This is what you're going to do again. Okay, if you have not done this, or if you didn't do this on the quiz, put a little note. Always start problems at an angle like this. Maybe it'll make a little help. Okay, maybe it'll help you clear things up. A lot of you started with acceleration, which is fine. You can do that too. But always have the components written. So you have one with a cosine and one with a sine. If you mixed up your sine and cosine, you need to just memorize it. I can't really help you with that. Okay, it's alphabetical. X comes before Y. C comes before S. They're alphabetical. They pair together. Okay, yeah.
I thought for the velocity of the y there, it would be 0, so you don't have.
But what is this? What do I see? What does I stand for?
Initial.
Initial.
Oh, okay.
When is the velocity of the y 0?
At the top.
At the top. This is not initial at the top. Yeah. So we could say this now, and I should not put a bar over the vy, sorry. I just got a little bit excited there. Okay. The fy is definitely going to be 0. So again, the beginning of this problem is at the launch time. What's the end of this problem? What's the end of this problem now?
Very top.
Max height. Very good. Again, what am I doing? What's the word I used? I'm truncating or breaking the problem up into pieces. I'm saying, you know what? We did the whole problem already, and we looked at the full length of the problem to figure out, okay, what was the actual x value? We did all that yesterday. But now, my concern is with the max height. Max height does not occur at the end of the problem. It occurs in the middle of the problem. We need to make that our new ending point. We need to say, you know what? Our new problem, part B, I need to rethink this whole thing. And I need to ignore the rest of this. I need to ignore it coming onto the building or whatever ends up happening there. I need to ignore the second half of the problem and only concern myself with the first half. Write yourself a note, please. Whenever you're finding max height, only look at the first half of the trajectory. When finding max height, only look at the first half of the trajectory. This is initial, and this is final. And then the problem is over. Okay? Initial and final. Now, with that said, turns out we really don't even need the x direction. We don't need the x direction at all. And we don't have something like time. We're not sure of the time yet, so we can't really do much with it. X, we don't really know. We got 2.67 yesterday, but again, that's the full length, and this problem is not symmetric, so we can't assume that x is exactly half. It's probably going to be really close to half, though. It'll probably be very close to half of 2.67, but it's not going to be exactly in the middle because of the fact that we start at a certain height and end on the ground. So we're not really going to use the x direction for anything, so let's stick in the y direction for now. What's the acceleration in the y direction? Everybody. Okay, always, always, always. So look at what you've got. Now we finally get to use these other equations. We've got VF, we've got VI, we've got A. There are two equations that we can use now as a result. Two equations. Give me both. Tell me what they are. What are the other two equations we still have that we have not really used a lot of this year? We have not done much with these equations at all. I'm seeing the same hands. I'm asking you just to read off equations, people. Come on. What are the other two equations that we have not been really using a lot of? Gabe, help me out.
Is it VF equals VI plus AC?
That's one of them. Very good. Deirdre?
VS squared equals VI squared plus 2AX.
Good. And since I'm in the y direction,
A Y.
I'll use a y there. Now, look what I did. I didn't put any subscripts. If you don't want to and you're getting confused with them, you don't have to, but I do like to. So what I'm going to do is this. I'm going to add little y's so I know that I'm in the y direction. Even though I know I'm in the y direction because I'm under the y column. So if you don't want to put these little subscripts, that's all right. But recognize that this VIY is 5.24 sine 55. It is not just 5.24. Is that clear? This right here, this value, one sec, George, just see it. This value right here, VIY, is this number right here, the whole thing. Do not just use 5.24 here for VI. That's why I'm specifying a little y there. Some of you are not using these second subscripts, and you put a VI there, and then since VI was 5.24, you might be tempted just to use 5.24, but really this is the velocity in the y direction initially, which is this whole thing.
Is when finding the max height, is the final velocity always 0?
Yeah, because at the top in the y direction it stops. Okay? So if you want to write yourself a note about that also, that's great. When finding max height or time to max height, set VFY equal to 0. That's your go-to thing to do every time. Because now you've got everything. All you don't know is t and y. All we don't know is t and y. We could solve for time to max height. Let's do that also. And let's see if that's half of what we got yesterday. We got 0.89 yesterday, right? So it should be around 0.445. But this is not perfectly symmetric, so this time might not be exactly half of 0.89. If this problem were from beginning to end, and the whole problem took 0.89, then the halfway point should be exactly half of that. But this is not perfectly symmetric.
But like, you wouldn't need to find how much you would really ask, right?
No, but maybe I give you a whole other problem. And if you look at the 8 or 9 examples I just emailed out, there's 1 or 2 that says, like, find the time to max height. Go ahead and use this right away. Jump right into this formula and use that. It would help you. Okay? So let's go ahead and figure this out. We want to solve for y and solve for t. Okay, I don't need the x direction anymore, so I'm going to go ahead and do this, if you don't mind. I'm just going to do my work over here. This is still the y direction. Okay? So if I want to solve this formula right here for t, I could plug my numbers in, or I could solve generically. Either way works. To be safe and be easy, I'm going to plug numbers in for now. But if you think that you're getting this stuff, I encourage you, when you're writing right now on your own, solve in the formula only, and then plug in numbers. Okay, so if I plug in numbers first, I'll have 0 for VFY. Oops. My iPad just froze completely. Or my pencil died. Tell me. Anybody have a stylus, an extra one right now? It doesn't matter if it's new, used, anything. Just for a little while. This needs like 5 minutes. It'll have juice in it.
Yeah, I have one.
Is it sharp? Can you just toss it? I'll catch.
Sorry.
I won't catch. No, that's not you. That's me. Sorry. Perfect. Thank you. So in the y direction, we're going to set... Okay. So we have 0 for VFY right here. For VIY, we know the initial velocity. What was that number? Anyone have that written down? 5.24 sine 55. What was that? 4.2? So 4.3, I'll say that. So 4.3 goes in for VIY. Acceleration is negative 9.81. And then t goes there. Solve for t, please. Solve for t. For those that wanted to do this with all variables and not plug in numbers till the end, I'll do that also. I'll put that approach over here in red. It would become VFY minus VIY equals AYT. And then you would divide by A on both sides. So that's the approach algebraically. So this would be the answer. But look, it's the same answer, right? Plug in what here? What goes for VFY? 0. Then you plug in VIY, and it's like when you subtract it, doesn't it become negative anyway? And then aren't you going to divide by this number here? That's divided by that number. So whether you plug in numbers at this stage right here, or you plugged in earlier and solved, you get the same answer. What does time turn out to be? What do you got? 0.43, agreed?
4.3 is
Now, that number is almost half of our number from yesterday. Take 0.89, divide 0.89 by 2. 0.89 divided by 2. You should get 0.445. That'd be my guess. And look at this number, 0.43. Why is it a little bit off? Because it's not perfectly symmetric. It's not. This problem started at a certain height. If this problem had started at the ground, the answer for this would have been exactly half of the answer for the full time. Yes?
When you cancel out the VFY, doesn't that also lead to negative, though?
It does. Look, negative, and isn't A negative also?
Oh.
Oh, there it is. Okay? A lot of you guys are forgetting that acceleration is negative. I've seen that a couple times, so be careful, please. It would be a negative over a negative, giving you a positive time. Do the same thing over here, please. Use this equation now. Use this equation. Either solve it for y like I did here generically, or plug in your numbers and then solve for y. Tell me what you get from that. So again, you're solving this equation for y. Either solve it by plugging in numbers, the negative y, or solve it first and then plug in numbers. Whichever way you choose is fine. It's right here, 4.3. VIY is 4.3. Here, Trey.
Okay. I was just,
Is it a question?
yeah, I just was wondering what VI was.
Yeah, so remember it's 5.24 times the sine of 55, which is this number here. That was VIY here. It's the same number. These formulas are very similar. Have you noticed, guys? You use almost the same variables the same way through, except you got a 2 here, and you got a y instead of a t, obviously, and those are squared. But the generic setup is the same. You're going to get 0 on one side again. Now remember, you are not taking a square root in this problem anywhere, because you're not solving for VI, you're not solving for VF, so there's no square root necessary here at all. You're squaring stuff, but you're not taking the square root. And notice that in some of your notes, when you guys see squares, a lot of you try to square root stuff. If it's a number squared, just type it in your calculator and see what that number turns out to be. See if I have any juice on this iPad pencil. Ooh, 28%, I'm good, I'm back.
Where do you see that?
You just swipe down from the top,
Oh.
and you can see the pencil charge, how much it's at. Can you pass this back to John? Thank you, John. So we take this equation, 0 squared equals 4.3 squared plus 2 times negative 9.81 times y. You can't forget the negative there, guys. You can't forget this negative. Because your answer for y has to be positive here. It's the height of the building, isn't it? It's the height of the building. It's got to be positive. So when you move the 4.3 squared over, it's going to be negative divided by another negative. What does 4.3 squared turn out to be? 18.5. Now, 2 times negative 9.81 is 19.62, and that's going to be negative. Okay, if you need to do this along the way with me, go ahead through it. Negative times 2, put the negative there, double it. 19.62 is double that. This is that squared. Move 18.5 over by subtracting 18.5.
What?
Yep, we'll get to that. We'll explain why. We divide both sides by negative 19.62. Cancel, cancel. What did you say, Jan?
0.94.
0.94? Is that correct? 0.94, is that what it comes out to? Let's talk about this answer. It totally makes sense. Remember guys, we're not on the problem where we're finding the height of a building anymore. I apologize. I said building a second ago, I think, right? We were finding the max height of that experiment in the back. So the answer has to be positive still, though. Okay, you get the idea of what I was getting at there? Y has to be positive. This projectile was launched from here, remember, from a height of 0.146, and landed, all the way over here on the ground. We are trying to find out this height right here. Okay, that's our goal, to find that max height. So the answer had to be positive. 1 meter. 1 meter, Plaza, behind you. In that cabinet, grab a meter stick real quick. Let's see what this looks like. Let's make sense of it. So 1 meter is considered the max height. So we'll just stand it up on a desk on its side so we can see what 1 meter looks like. Stand it up right on your desk there. So that's a meter. Take a look. And if you think back to yesterday, when it was launched at 55 degrees, it attained a height of about a meter, or 0.94. Okay, make sure your answer makes sense. Some of you on the quiz answered with the building height of I think it was 4,000 meters. That's 3 miles. A building 3 miles would not stand. It wouldn't be able to stand. Thanks, Bob. Okay, so you have to make sense of your numbers. And we're going to talk about this all year long. When we get to forces and mass, you have to have a good number sense. What is 2 newtons? Or what is a kilogram really? You know? So when you have numbers as an answer, make sure those numbers actually make sense. Okay? Actually make sense.
Oh, I did it was I saw it for what? You can see that except squared and A is 2. If you saw it for y.
Yes, you would have squared, and 2. Yep, that's exactly right. Okay? Good. I want to also continue now, and I want to talk about a further extension. We have a couple minutes still. I want to talk about a further extension of this idea. What if I wanted to find out, what if I wanted to find out the velocity upon impact? Remember when it hit the desk and it made that noise? It had velocity when it hit the desk. The question is, how do we find that final velocity at the end of the problem? So it's already been launched, it's through the air, It pauses for a second vertically. It's still moving this way. It then starts to pick up velocity negatively while still moving that way. It hits the ground. The instant before it hits the ground, I want that velocity. Let's figure out how to do that. Do you know how to do that? You want to give a suggestion?
You basically kind of keep the table, except now the initial velocity is 0, and then final velocity you don't know, so you have to look.
So where are you starting this problem? To make initial velocity 0, where do you have to visualize the problem beginning now?
At the top.
At the top. Very good, Ernest. He's really working hard on this. You can see that clicks, right? Look, guys, at the top. Start the problem up here now. This is initial. Make the ending final now. So let's draw a new diagram. Make this initial and make that final. I can do that. I'm allowed to do that because look, if I know that now VIY is 0, we'll call that the beginning of the problem, and our goal is to figure out what is VFY. We know V bar X, that is not changing, it's the same. What was that number? What was that number? 5.24 times the cosine of 55. What did we have from yesterday?
4.3.
Oh, that was the Y direction.
Oh, for the X.
What was the X?
2.98.
This was the number we got the other day, and this is the number that's going to be the whole time through. But our goal is, can we figure out this number and then put these together? Because remember, this is the X component, this is the Y component. We're going to have to use a little bit of trig with Pythagorean theorem to do that. So now visualize this problem starting at the top with no velocity in the Y direction, ending at the bottom. We can calculate the Y velocity as a result. How far does it drop? How far does it drop? How far does it drop? 0.94. Where's George getting that number from? It's the max height. You're starting at the max height now, so Y is going to be what though? It's dropping. Negative. Okay, so here's our new problem. Forget the old problem. We're beginning a whole new problem here. And the Y value is negative 0.94. We have Y, we have VFY we're looking for, we have VIY, we have acceleration. We could solve with the same exact formula. Ernest?
So if you're looking for right with the velocity right before it hits the ground, it has to be part of the whole problem, where you grade it as 2 low.
Or you just, if you know the max height, you can do it this way too.
So,
You need to have the max height to do it like this though. You know what I'm saying?
Yeah.
Or, Ernest, if you knew the time it takes for half the flight, you could use VF equals VI plus AT. You know what I'm saying? If you know that, say you knew half the flight was only 2 seconds, you could use VF equals VI. I'll finish this tomorrow. Or actually, I'll see you guys on Friday for this. What is due on Friday? Okay, your projects. You need to be testing this stuff. When you come in, we're going to spend probably the whole period Friday doing this. We're going to finish, well, I guess we'll finish this problem off maybe next week on Monday or Tuesday before our test. Review is Tuesday, test is Wednesday. Okay, keep that in mind. Keep that in the back of your mind. You should be starting your problem set questions for 4-4. You should also practice those 8 or 9 problems I sent you. Try to finish this today. Yeah, for about 30 minutes. Right? The max height from the last part of this problem when we left off yesterday, the max height was 0.94 meters. So we know that this is going to drop 0.94 meters now. So that's our Y value. You could actually think of this problem like a horizontally fired projectile problem. So think back to yesterday. The actual problem began here. The object was launched. It reached max height. We looked at the first half of the problem yesterday, and we determined the max height available, the time it takes to get there, and then afterward, we said, you know what, now we're going to try and figure out the second half of the problem to determine the impact velocity. So we're starting the problem up here now. This is my initial spot at the top. This is the final spot at the very end. Our goal here is to figure out VFY. Why is V bar X a constant again? I've talked about this many times. Why is this a number that we know is the same from the beginning, in the middle, at the end? It never changes. Why is that? There's no acceleration in the X direction. So this would be our velocity in the X. So when this projectile hits the ground, this is what's going to happen. It's going to be moving this way, and it's going to be moving this way. And our goal is going to try to be to find out whatever that vector length is, like this. So what we could really do is we could take this vector right here and slide it over here, and you end up with a triangle. So at the end of this problem, when we're trying to figure out what the overall velocity is, we'll have Vx, We'll determine VFY, and then we'll use these two together with Pythagorean theorem. And this is back to like the 4-1, 4-2 stuff, where we try to find out the resultant. So what we need to do is determine what this VFY is, which means we have to figure out what do we plug in for these variables in the right spots. So we think of the problem as starting at the top. So your initial velocity is like 0 in the y direction. Remember, it's only moving, so it's moving like this, and then it stops in the y direction. So we'll call this the beginning of the problem now. So it's got no velocity in the y direction. So this is going to go to 0 right here. The final velocity is what we're looking for. So we're going to leave that alone. We don't know what that is. Acceleration is always the same. And then the y value in this case, notice, is negative. Why is it negative? Why is the y value negative? Yeah, it's going down. So this object's going to start at a peak. The peak height is 0.94 meters. I talked yesterday in the other class about something about vocabulary. You need to know vocabulary. So if I use the word, well, actually, let me ask you. What are some words that mean peak or max height? What are some other words for that? I just use the word peak, right? It's a synonym for max height. What are some other words you might talk about to represent the top of a parabola or a curve or some sort of an arc? What word might you use? What is it? Climax. Pinnacle. Vertex. Apex. Maximum value. Turning point. All those words are really just talking about the very top of the path. So when you have your test and it says, for example, find the time it takes the projectile to reach its apex, you should know that apex means top, okay? Top of the path. Or time to max height, I might say. But understanding that those are all synonyms of one another. Negative, negative makes this what, obviously? And we need to have a positive, because actually you guys know this. In your math class, don't you have a test today?
Yeah.
And aren't you doing stuff with imaginary numbers? Yeah. Well, here, if I make this is a squared, right? So I have to square root at the end. If this were negative, the answer would be imaginary, wouldn't it? So that's why these two negatives are going to become a positive here. The answer has to be a real number. You don't get imaginary answers in mechanics. You do in other types of engineering and physics, actually. This is going to be 19.62 times 0.94. What does this number turn out to be right here? What does that number become? 2 times 9.81 times 0.94. What do you got? Who's got it? 18.4. Now, I'm looking for VFY, so I take the square root of that. And again, from your math class, I know you guys have been studying this. You need to recognize that when you take a square root in an equation, the answer has plus or minus written next to it. The answer always has plus or minus. Okay? So, which of these answers am I going to choose? Am I going to choose positive or negative? Positive or negative? Which one, Will? Positive. Why positive, Will? The problem started going up. It started going up for sure. Gabe?
It's not real, it's negative.
Negative? Why negative?
Because you said, well, when you're looking for...
Which one am I choosing here, remember? Am I choosing positive or negative then?
Oh, negative, because it's going down.
It's going down.
Yeah.
The projectile is falling down, and the velocity that we're solving for is in what direction? Isn't it the y direction? So because this particle, if I go back up and look at this, because this particle is moving and it's falling down, the velocity in the y direction, look at that arrow. That arrow is down, isn't it? That's the vector. That's how fast it's going down. It's a negative velocity, it turns out. So the answer for VFY turns out to be a negative number. And that's going to be around what? 4 point something? 4.3? What do you get for this? What's 3? Okay. Something like that, right? All right, 4.3 meters per second. Now, this is the velocity that the particle has in the y direction. In the y direction at the end. Okay, so here we are. Here's the ground. Here's the particle. It just took the path to hit the ground. At the end, we represent its velocity with a vector of which length has 4.3 down. What is the x velocity again? Go back up, scroll up, and find your v bar x. It's always the same number at any given instant in time. The velocity in the x is always the same. What do you have in this case? What was the velocity? Was it 5.2? I don't think it was. It was something like that. 2.9 something. Right, let's go up and look. Oh, there it is. 2.98 v bar x. 5.2 was vi. Okay, v bar x was 5.2 times the cosine of the angle, which gave us 2.98. So that's 2.98. Let's draw that vector here. So we take a look. The AirPlay is not responding. Give it a sec. So yeah, there it is. 2.98. So we see that vector in the x direction. So what does this mean? What does it mean? If I were to think about this projectile, can I use this? Might be loud actually. Yeah, but I'll say. If I were to toss this projectile, right, and I just lightly toss it, yeah, it's loud. When I hit the ground, why is it continuing to move that way? How come? Because it has velocity in the x. Well, it also has velocity in the y. Why didn't it stop? Why didn't it continue going down? Because what?
The ground.
The ground. The ground stopped it. Was there anything to stop it? No, and then it hit the wall, so it stopped. So when I tossed this a moment ago, it was not only moving down, because it's falling, but it was also moving to the right. Does everybody see that physically? As it falls this way, it's moving both that way and down. That's what these arrows are showing. This is saying it's moving to the right with a velocity of around 3 meters per second, but it was also moving down. Why did you hear that noise? The energy from the velocity here was converted into sound energy. That's really what's happening. We'll see that later in the year. But I want you to see that this number isn't changing really, because it continued to roll that way until it hit the wall. So your Vx isn't changing as it moves through the air. The Vy is what's changing, right? So it has positive velocity, hits the top, 0. On the way down, negative velocity. It's the same thing as if I toss it from here to here. Positive, 0, negative for the y direction. The x is always 2.85 to the right. Nothing is ever slowing it down to the right. So we take these two numbers and we want to figure out, well, if it's moving to the right and down, then really this is what it's doing. That's the actual vector. AirPlay's not working at all. Give me a second. You're right. So you take a look at this and you say, to find this length of this vector here, this is 2.98, this is 4.3, right? I don't care about the negative because I'm going to square them, right? 2.98 squared plus 4.3 squared equals VF squared. And then solve for VF, your actual velocity.
Could you connect the end of 4.3 to the end of...
Here?
I mean, like this, like wouldn't it be like the same thing?
It turns out it would, but because the nature of the problem is to the right and down, I'm going to draw it that way.
Yeah.
Just to show the direction it's impacting. But yeah, it would be the same number, yep.
Could you also find the area, since it's a square rectangle, and then just cut it in half?
But what would the area do for you? We're not looking for the area.
No, I know, but aren't you trying to find that?
We're trying to find the length of VF, the diagonal length.
So let's say you were to multiply 2.98 times negative 4.3 split it in half.
But that gives you the area of the shaded region. That's not what we're looking for. This is not, you're confusing geometry with this. Right now, I want you to think about this. We're talking about vectors. Vectors are lengths. They're not areas. So if I want the length of that black vector right there, I take 2.98 squared, I take the height squared, and I think about this as a right, look, turn it on its side. Maybe I'm not showing this properly, sorry. This is a right triangle. Turn your head if you need to, guys, but there's the right triangle. Do you see the right triangle? That's what I meant by Pythagorean theorem. 2.98, take the 4.3, write that in right there. Even though it's negative, I'm doing the length because I'm going to square it, right? 2.98 squared plus 4.3 squared equals that diagonal squared. So what I'm doing is the opposite of the cosine sine part. Do you remember in the beginning of the problem, we started and we said the velocity was 5.2. So to find v bar x, we did 5.2 cos 55, or 65, whichever. And then the other one we did 5.2 sine. And we broke up the initial velocity into its components. Now, we're taking these components at the end and we're coming up with the final velocity. This is the opposite of breaking up your initial velocity into Vx and Vy. It's putting Vx and Vy back together into a final velocity. What do we get as a number? Maybe this will help with a little bit of understanding if we can get a number at least. Remember, I'm squaring a negative, so that's definitely positive. I hope you all see that. We're squaring a negative 4.3. What do you get?
5.23.
5.23. Coincidence? Coincidence? What do you think? If I hear that again, you know it's going to be a problem, guys. Seriously. 5.23 is the VF. 5.23. What was the VI that we started the problem with? Go back up to the very beginning of this problem if you have to. What was the VI that we started this entire problem with? 5.24. 5.23. That's not a coincidence. The initial velocity should be close to the final because it was almost symmetric. Do you remember? Why did I say almost symmetric? It started at a height of like 14 centimeters, the projectile launcher. It launched from the projectile launcher and it ended up on the table. So it did lose a little bit of height on the way, or gain a little bit of height, I guess, on the way down. So this answer may be a little bit different, and there's obviously a little bit of air resistance, so realistically, this number could be different. But theoretically, the number should be the same thing if it were perfectly symmetric. Okay, it's not a coincidence that this comes out to be the final velocity at the end of the problem when it hits the ground. There are other ways to ask questions like this. I could ask you to find the velocity at any given instant in time. And at that instant, what you have to do is find the VF in the y direction, and then use the x component of 2.98, and do this again. So let's practice something like that real quick. Okay, so let's say we've got a problem that looks like this. Let's say that an object is launched from the ground. It gets to a height of, let's say the initial velocity first is 4 meters per second. It's launched at an angle of 60 degrees. It gets to a height of 12 meters. Will it be able to? No, it will not be able to. Let's go with 40 meters per second. So initial velocity of 40 meters per second at an angle of 60 degrees. Now the question is, determine the velocity of the particle when it reaches 12 meters height. It's going to go beyond 12 meters, I'll tell you that right away. Think about it, because after a second, how far would it actually go? Not really, but you want to think about 40 meters. It's at an angle, so it's not going to be 40 meters. But when you think about it, it's going to easily clear 12 meters. That's why I changed that number from 4 to 40. Okay, this will easily get to a 12 meter height. My question for you is this. Yes, it will continue, and it may go further. But I want to know, at that instant, at 12 meters, what is the velocity? And I need to do this again, the same way I just did the last problem. I need to think about the fact that Vx is always the same, so we can figure that out. But then we have to find Vy at that instant, and then combine them again with Pythagorean theorem. So let's go ahead and break this problem up. What do I have in the x and the y direction? What are my x and y values? How do I get these? Right away, guys, these should be automatic. I mean, this could be any problem, you can give me the answer to this. Even if you did not know anything about this problem, you should be able to fill in these blanks automatically. John, go.
Actually, no, I was going to say for acceleration, I was going to say 0.
That's fine. That works. And what about the y direction?
Negative 9.81.
Very good. Okay, what else? What else? Somebody else help me? Let's take it.
So you do cosine of 4, or 60 times 40.
Yeah, so let's write it the right way. Say it that way, okay? Always trig function after. It's just traditional way. It doesn't matter. Ryan, the other one?
40 sine 60.
Okay. That's our givens automatically. You're going to answer your question.
Yeah.
Okay, those are givens automatically right away. Now, the question is, determine the velocity when it reaches a height of 12 meters. It's going to go beyond 12 meters in height. If 12 meters were the apex, well then the vertical velocity is just 0. And the horizontal velocity would be whatever v bar x is. But it's not at its apex. It's not at its peak. So we need to actually figure out Vy at that instant and Vx at that instant, both. Well, Vx is the same throughout the whole problem because acceleration is 0. So just tell me what 40 cosine 60 is, please. What's 40 cosine 60?
The y is also 12.
What is 40 cosine 60 first? It's just 20, turns out. Cosine 60 happens to be 1/2. It's one of the interesting angles. So this happens to be 20. That's v bar x right there. What's VIY? What's 40 times the sine? 40 times the sine of 60. 34 or something? 34.64. So, does this projectile have more velocity in the y or the x to start? Where's the velocity mainly for this projectile? Is most of the velocity in the y direction, or is it in the x direction for this problem? Look at your numbers and just compare them if you have to, or look at your angle, right? Or your angle. Same hands, come on. This is not too difficult a problem. Is there more velocity in the x or more velocity in the y to start the problem? Good.
The Y.
The y. 34.6 is greater than 20. Or you look at what? What's the other factor? The degree. It's more than 45. When this angle is more than 45, most of your velocity is up. When it's lower than 45, most of your velocity is out, or in the x. So in this problem, we have most of the velocity in the y direction. All right. Now, this is not going to change. Vx will never change. So at that instant in time, let's draw a little vector for Vx. Velocity in the x at this instant is still going to be 20 meters per second. That's the velocity in the x. But our question is going to be this really now. What's the velocity in the y at that moment? Am I going to call that initial, final, nothing? What am I going to call that? What do you think, Matei? Why final?
That's the last or end of the problem.
That's the end of our problem. That's exactly right. That's the end of our problem. We don't care about this problem after 12 meters. It says, find the velocity once it's reached a height of 12 meters. So after 12 meters, who gives a crap? It doesn't matter. It doesn't affect it at all. So we care about 12 meters. So we'll call that final now. And obviously this over here was our initial. So we've got VIY initial, right? This is the y velocity initially. We're looking for the final y velocity. We've got the acceleration. We need one more piece of info. One more piece of info. What is that last piece of info?
We always need time.
Oh, actually, we don't in this case. That's, you know, you said we always need time because every problem we keep doing is involving time. This time we don't need time. This time we don't need it, actually, it turns out. What do we need instead?
X?
Not x. Not x. Y.
Oh, I thought we put Y as 12.
Well, I'm saying, sorry, I apologize. We need to list it. That's what I mean, to help us with the variables. Sorry. Yeah, it's on the, you're right, it's on the diagram. I meant as one of our givens. Yep. So, it turns out that for a problem like this, we don't need time and we don't need x because we're not being asked about how far does it go. We're not being asked about how long does it take. What are we being asked? What's the question? What's the question here that's being asked? We got to know the question to have the answer. Only 3 people know what the question was. What was the original question? Right?
You want to find the final velocity when it's
Yeah. Find the velocity when it's reached a height of 12 meters. It never says to find how far it's traveled horizontally. The problem is not necessary to find time at all. We don't need time here. It doesn't say how long does it take. It says find the final velocity or find the velocity at 12 meters. So let's find the y velocity by using our equation. Okay, there's our equation. Vf squared equals Vi squared plus 2ay. I'm using subscripts, obviously, to indicate that this is the y direction for each time. So the problem started with our initial velocity. We have our y velocity from that part. We always do this to start. 34.64, that will go in right here. That's initial. That's going to go in right here. We're looking for Vfy. We've got acceleration. That comes in right here. The height we're looking to attain is 12 meters. That goes in right here. So plug in for these 3 variables. Okay, plug in for all 3 of them. And see what you get for Vfy. So recognize here that you're going to have a negative part under the radical, but our assumption is that the positive part will be greater than the negative. If it turned out not to be and you got an imaginary answer, it would have meant that this projectile would never reach 12 meters. Okay? Again, just to give you an idea, a little understanding. If you end up getting a negative answer here, it's imaginary, meaning it's impossible to even get to 12 meters. That's what the significance of that would be. You could not attain 12-meter height. But we can attain a 12-meter height because we had a lot of initial velocity. This positive number will be around 900 and change. That will exceed this number dramatically. Okay, what do we get? What do we get for VFY in the end? And please take the square root of whatever you get underneath. So you get an answer, take the square root. What do you get? 31.1. Can I get nods of yes or no?
I'm confused because I got negative inside of that.
Well, that means you made a mistake. This needs to be squared. Did you square this?
1,199.
All right, then you should have minus 2 times 9.81 times 12.
Yeah.
Or plus. Put a plus, but there's a negative there. Just move the negative out.
It comes out.
Yeah, it's still going negative.
Yeah, this part is negative right here. But this is much bigger and it's positive. So you got to take 1,000 here, and this is going to be 9 times 12, right? 9 times 12 is only like 100. Times 2 is like 200.
This was 1,000.
It's going to be 1,000 and then like a negative 200. Same thing? Again, look at this. This number will be around 1,000, right? And this will be around negative 200. So this will be positive in the end still. Okay, even though part of it was negative. So that's our velocity in the y direction at max height. So why is that number less than 34.64? How come that number is less than 34.64? What's happening on the way up? The projectile is slowing down. Think about it logically. You toss an object in the air, as it gets to the top, it slows down. So the answer that we got at 12 meters should have been something less than what we started with for certainty. It had to be less. If you got a number greater, it wouldn't have made any sense. Okay? So this is not much less, actually, it turns out, right? It's really not much less than the 34 was here. But let's see what significance that has. So 31.1 goes in our diagram. Let's go back to our diagram now. That goes in for VFY at the top there. 31.1. So we've got our velocity in the y. We know that the x velocity is 20, the whole problem. It never changes. It's a constant always. It's v bar x for a reason. So we now have our x component and our y component. Let's go ahead and use Pythagorean theorem. Let's go ahead and use it. Take 20 squared plus 31.1 squared to get the overall velocity. And I'll draw that in so you can see it. There's the overall velocity we're looking for. And if you need to draw a triangle, make a triangle out of it, use dashed lines to show that. Okay, take a look. 31.1 is the vector length on the top. I'll make it more obvious. Hold on. Okay? So the y velocity is 31.1. That's what we just got as an answer from this part. We know the x velocity is always 20. What do you get, Ron? 37? Again, the answer had to be less than what you started with. And what did we start with for the overall velocity for this problem? 40. The overall velocity at the beginning of the problem was 40. So the overall velocity, I say overall meaning not x and not y, but the actual velocity, had to be less than 40. And our answer is approximately 37. Where does that come from again? Okay, I want you guys to see that this is not, please look. This here, I'm just going to I'll box it in red actually so you can see what I'm talking about. This is not a formula from physics. This is math. This is not VF squared equals VI squared and stuff. This is not a formula from physics. I'm simply completing the triangle. Okay, look at the triangle at the top there. 20 squared is the base. 31.1 squared, that's the height. And that equals VF squared. That's all that is. Okay, it's not a formula from physics at all. And that's where this answer for VF comes from. When we solve for VF by taking the square root of those squares of sum of squares there, you get 37 meters per second. We've got about 10 minutes. I'm going to vary up another problem. I want you to try with the person next to you. Okay? Just try it for a little while. Try to get a head start at least. Try to list your givens. See what you can do. But here's what we're going to say for this problem. We're going to say... an object is launched from a height of 20 meters. You could write the words down at least if you want to, or you could draw a diagram. Depends on what's more useful for you. An object is launched from a height of 20 meters with a velocity of 30 meters per second. I shouldn't even write VI. I should just let you guys figure that part out. With the velocity of 30 meters per second, and it's launched at an angle of 25 degrees. An angle of 25 degrees. Determine the velocity of the object. Determine the velocity of the object when it reaches the same horizontal location it started at. Determine the velocity of the object when it reaches the same horizontal location that it started at. Then determine the impact velocity when it hits the ground. Parts A and B to this problem. So part A would say, determine the velocity when it reaches the same horizontal location it started at, and then determine the velocity when it hits the ground. Okay, try to set it up. Think about the last two problems we just did, and try to utilize that information to help you with this. I'll give you maybe like 4 or 5 minutes just to start it up, and then I'll go into the analysis that I would take to do this. Determine the velocity first for A when it reaches the same horizontal location, and then also determine the impact velocity when it hits the ground. Try it again, list your givens. If you need to talk to the person next to you to check, that's fine. Impact velocity. The method of solution is pretty much the same for both of these parts, FYI. So part A and part B have the same approach, just with something else that changes. Is this problem asking for time anywhere? Is this asking for X anywhere? Good. Right away recognize that. It's not asking for time, it's not asking for X. So So you're probably not going to have to do too much in the x direction aside from finding v bar x to start. What is v bar x to start? What is v bar x? Ernest? 27 point? 18. Got it. Okay, Ernest gave us v bar x. Should have that right off the bat. Write that down right away. Is that ever going to change? No, it's never going to change. Write it down if you don't remember that. It's never going to change. The rest of this problem, that's v bar x. It's not changing, hence bar. The bar means constant. VIY, VIY. 12.6. Agree, disagree? Yep. And it should be less than what we got for the other one. How come? Why is VIY less than that, than the value of VX in this problem? It's the opposite of the last problem, right? Why is this number now less than this number? What happened?
The angle is less than
45. Very good. It's a low angle. It's less than 45, so your velocity is more in the x direction now. Okay. Starting point, very good. Remember, those are the velocities at the beginning. So if you were to complete that triangle at the beginning, for those that are maybe a little bit confused still, take a look. If you were to make a triangle out of this vector, this length here, right here, that would be 27. That's the velocity in the x. And 12.6 would be this height right here. It's the velocity in the y. So the y is pushing up, the x is pushing out. It's pushing out with a velocity of 27.18. It's pushing up with a velocity of 12.6. Those are your vectors at the beginning. But I don't care about the beginning right now. I care about those other two instances. So I need to break this part of the problem up. The beginning, sure, that's fine. We know that. Where's the end of the problem for part A? For part A, Will, where is it? Yeah, it's right here, guys. This is the end of the problem for part A. Part A said, find the velocity when it reaches the same horizontal location. Well, that only happens once. Right there. What do I know about this particle at that instant? I don't know the x displacement. I don't know time, but I do know something. George?
Final velocity.
I'm looking for the final velocity. I'm looking for it, but I do know something else. Ernest?
No, y in that case would be 0.
Very good. Let's stop and listen to that. What is it again, Lazar?
0.
Y equals 0. Why? Why is that? Don't use that terminology. There's no vertical displacement. It is moving up, because I don't want to say it is moving technically. There's no displacement. It started here, and where did it end? Right here. Is there any change in height from here to here? No. What's the change? This is the only change you have, right? So if you start at this height, and you end at this height, y is 0. It's the same thing as if it started on the ground, and ended on the ground. Forget the cliff for a second, please. Imagine it starts on the ground and it ends on the ground. If there's a problem like that and you need to figure something out, the y value is 0. Please don't pack up. We got a lot of time still. 10:13, right? We want to see here, what is that velocity when it reaches that location? So for part A of this problem, we need to set y equal to 0. We need to set y equal to 0. Pencil just died. Are you kidding me? And acceleration again was negative 9.81. Now this is only for part A. Go ahead and figure out VFY. Use the same equation you just used for the last two parts. Go ahead and figure out VFY. Remember, that's what you're looking for. You're looking for the velocity when it reaches this location, which is the end of our problem. That's what we're looking for there. We know the velocity in the x. The velocity in the x is always going to be 27.18. My pencil's charging. Excuse my hand right for a moment. VFY, though, it's on the way down, right? So the velocity in the y direction is what we're looking for. This is what our question mark is. We're trying to figure out what that value is now. If we find VFY, we can use Pythagorean theorem again to figure out the value of the velocity. Mm-hmm. That's it. Yep. And now your goal is to plug in for VI, A, and Y, and then solve for VF. My handwriting, sorry. Again, this is terrible. Okay, that's the equation we're going to use again. VFY squared equals VIY squared plus 2AY. This is going to be 12.6 squared plus, this is going to be 2 times negative 9.81 times 0. So what happens to this whole part? Everybody see this, please. Look up. This whole part drops off. Y is 0. So this doesn't have any effect. So VF and VI, what happens? What can you say about them? They're equal. Look, if VF squared equals VI squared, then VF must be VI. They got to be the same thing, except for one difference. What is that one difference? There it is. VI in the beginning is going up, isn't it? And on the second part, VY is going down. So the answer that you started with of 12.6 for VI, VF is just going to be not 12.6, negative 12.6. You could plug in and check all this, but this is one of those times where the 0 drops everything off in that part of the problem. So if you need to write it, you can literally write this, but you should be able to see that since you're squaring both sides, the squares drop off. And since the answer would really be plus or minus, we choose negative for VFY because this particle is moving down in the y direction. It's moving down at the end of the problem.
So why would it be?
Why is this whole thing 0?
Yeah.
Because look at the displacement in the y direction. It was 0. Remember? It starts here in the cliff. It leaves the cliff. And it ends right here. That's a y value, a difference in height of 0. It started here and it ended here. There's no change. Well, 2 times 9.81 times 0 is just 0. It's the 0 product property, right? Anything times 0 is 0. So that whole entire thing drops off because one piece is 0 and you're multiplying. Nick?
Why do you drop the exponents?
How come these can cancel? Because both sides are squared. If I told you that 5 squared equals x squared, what's x? It's just 5, right? It's got to be. So whenever both sides are squared, you can drop both sides square parts. So if that's the velocity in the y direction of 12.6, that's going to go right here now. 12.6. Since it's negative, it goes down. Since it's down, it goes negative. But go ahead and use Pythagorean theorem on those numbers. 12.6 squared plus 27.18 squared equals VF squared. What does VF turn out to be? What does VF turn out to be there? What do we end up getting, Matei? You got what? 24.03? Definitely not. Negative squared is a positive. You forgot to square the negative. It should be. It can't be. Think about it. How could it be less than one of the two numbers given there? It can't be 24 if part of it's 27, right? What do you got, Ernest? There we go. Check it again. Look, Matei. Here's your vector, right? You got to do 27.18 squared plus 12.6 squared. The negative doesn't matter. You're putting the negative for sure. You're forgetting. You're squaring it. The negative has to go inside the parentheses if you're going to square it in the calculator, or just drop the negative altogether.
Still getting 24.
Okay, so see me after and we'll go over it. So VF turns out to be 29.95. Why is that so close to what we started with? What was the velocity to start this problem? The initial overall velocity to start the problem. It was 30. Brian, why is it so darn close to 30? Why is it so darn close to 30?
Because the original was 30.
And the problem is, what's the word? A parabola is by nature? So symmetric, good. Like a mirror, good. It's symmetric. You start at the cliff height. My first part of this problem was find the velocity when it reaches that cliff height again. Because of the symmetry, the answer was just 30. If you start with 30, you got to end with 30 if it's perfectly symmetric. To do the last part, we're going to change y here. To get the last velocity at the end, change this y value to negative 20. Change this to negative 20, because now it's dropped to 20 meters. Redo this, get a new number. Okay? Hey, so listen, on Monday we have a single. The plan is to do more example problems. The plan will not be successful if you don't do them over the weekend, though. You have a problem set, and you have 8 or 9 problems I emailed you. Get through that work. You also have your write-up due. Okay, you have your write-up for this due on Monday. Make sure you have that in. All I need is a page. I don't need more than that. If you put figures and diagrams, that's after the 1 page, okay?
Can I leave I can leave in this room until I come down to lunch?
Whatever's fine. Yep.